We have seen in the previous video that semiconductors have a band gap of 1 eV. However, let's ask ourselves if we can make them even better. If we can reduce the band gap even further to allow more increase in charge carriers for small increase in temperature. We do this by a process of doping. Doping is the process of adding impurity atoms to the structure of semiconductors. Doping has the effect of improving the conductivity of properties of the semiconductor. Let's see how this is so. And when this is done, when an intrinsic semiconductor is doped, we call this material an extrinsic semiconductor. So typical intrinsic semiconductors are the silicon semiconductors. It will be a grid of silicon atoms forming pair bonds with 4 other silicons. If we remove the central silicon atom and we input in a group 5 atom, which in this case is phosphorus, we see that there is a free electron around. This free electron is loosely bounded to phosphorus, and hence it's easier to cause these free electrons to move away and hence conduct electricity. At this point, I would like to remind you that this semiconductor, even though it's doped with phosphorus to allow a free electron, the charge is still neutral. This is because although there's one more free electron, phosphorus also contains one more proton to allow the net charge to be neutral. So once we have doped silicon with a group 5 atom, these atoms are able to donate their electrons easily because these electrons are loosely bounded. So these free electrons do not mean that they are actually fully free. Now, because most of the charge carriers in this case are negative and electrons, we call them n-type semiconductors. And in the energy diagram below, we see that the group 5 atoms introduce a new energy level just below that of the conduction band. And this energy level is called the donor level. We call this group 5 atoms the donor atoms, which causes the donor levels. What does this mean? It means that at this level, there are many electrons with these energies ready to cross the small and new band gap into the conduction band. This new band gap is very small. It's only 0.05 eV. Right, so once again, an n-type semiconductor is doped by group 5 atoms. These donor atoms creates a new energy level filled with electrons ready to cross the band gap of 0.05 into the conduction band and hence conduct electricity. Right? Because the band gap is only 0.05, even small temperatures are able to bump these electrons from this level to the conduction band. Hence, doping intrinsic semiconductors increases the conductivity of the material vastly. Now let's look at p-type semiconductors. P-type semiconductors are semiconductors that are doped by group 3 atoms such as boron or aluminium. When we dope this silicon with group 3 atoms, because they only have 3 valence electrons, there will be a hole created. This hole attracts that of the electron because it is whole, it wants to be filled up with an electron. So this, because it wants to accept an electron, these are called acceptor atoms, right? And it will try to make up for the shortfall of the 4th atom. Because most of the majority charge carriers are positively charged holes, the semiconductors are called the p-type semiconductors. If we apply electric field from right to left, the hole will be moved towards the left in the direction of the electric field. In short, the hole behaves like a positive charge. Because it is an acceptor atom, it creates an acceptor level energy, which is empty and able to accept electrons readily. Because of the small band gap of around 0.05 eV, electrons can easily jump over from the valence band when there are small thermal excitations, allowing an electron to conduct electricity in this level and also leaving behind a hole that can also conduct electricity.